Hello, welcome to this video in which I present a hobby project I did, which is classifying objects based on their geometry in real time using neural networks. So let me right away give you an impression of what that is. What I want is when I put an object in the scene, I wanted to recognize this as a Buddha statue, for instance, or any other object for that matter. And for this, which is a watering can, I would like to label it as a watering can. So what you see here on the top left is just a regular webcam, which is not involved in this processing of the images, but it's just for your reference. Below that you see the control panel by which I can control image filtering and other things. And on in the middle and on the right you see depth images. So the center image is what the depth cam is seeing, which is unfiltered. And on the right you see the result of the filtering, which is applied. So to make this work, first need to record the background of the scenery, which is this. This is just static. I'm not interested in this. So therefore first recording the background as it is. Stop recording the background and you see there are still some tiny specks left. Applying a filter to that. Before sending this data to the neural network, it needs to be centered. The data needs to be centered, so that's what I clicked here, shift to center. It makes the whole application insensitive to where an object is put in the scene. And next I'm going to ask to classify objects, and this is also a noise filter which I put to max. So now I put the object in the scene, and it takes a bit to load. Here it is, Buddha. As you can see, it doesn't really matter where I put it. Well, I need to put it at least in its view, of course. You see that it finds the Buddha, it centers the data because the black box on the right, you see that Buddha is always in the center. And it labels it as Buddha correctly. Now when I put in a second object in the scene, you see that it sees this as a watering can. So also with this, you can put it into several locations as long as the objects don't overlap. It finds the two objects, cuts them out and labels them each. Let's get back to the presentation in which I will tell how I got to this result. So first overview of the project and some texts, some prerequisite knowledge before getting your hands dirty with these neural networks that I think are important. If you want to take this kind of projects on yourself. Next I will explain the application architecture by using a sequence diagram, an overview, and zoom into the image processing in the sequence diagrams. Then I go into the image processing steps in more detail by explaining in chronological order what they're doing and why they are needed. Then I explain a bit about the neural network, its architecture, how it's trained, and that you can use real or virtual data. What I mean by this, I will get to that. So an overview of the project. So the end goal was classify objects based on their geometry. And that's different from using a regular color image or a color webcam. That is, depth images are basically just also 2D images, as you just see, they are grayscale, but each pixel doesn't represent color, it represents the distance relative from the camera to the object. There are a few advantages of this. The depth cams have their own infrared laser grids, so you can put this whole setup in the complete dark and it will still work. And an advantage of this setup is that it only cares about geometric information, so surface texture is irrelevant, and I'll show you that by picture. So on the left here you see the grid that I just mentioned, or it's a matrix. And on the right you see some bulldogs. Well, these are basically all the same in geometry, but they have vastly different surface textures. If I see this bulldog with the red and yellow paws, I wouldn't even recognize it straight away as a bulldog if it wasn't standing between these other bulldogs. So this setup with this depth camera doesn't care about that surface geometry. It will just recognize it as a bulldog because it has the shape of a bulldog. Also, some disadvantages of this setup is that shiny or completely dark or furry or spiky objects are difficult to measure because it's difficult to capture for the depth camera. Dark objects completely absorb the infrared light and don't reflect, so goes into the void. And as you've seen, the depth camera is pretty high in noise compared to a regular color camera. The techniques used for this entire setup is Python as the programming language, TensorFlow Keras for the neural network, depth camera, and the OpenCV library for image processing. So some prerequisites in knowledge that I think is good to have before getting your hands dirty with anything related to neural networks and images is a little programming experience, preferably in Python, because a lot of these neural network packages come prepped for Python. Python is the language to use for neural networks. Understanding of what the dot product means in mathematics, and then based on top of this dot product, also understand the concept of convolution, that's sliding a smaller matrix on top of a larger matrix, applying the dot product, and that gives you a sense of similarity. And that in 2D because we're working in 2D images. So the application architecture in a sequence diagram. First we have the camera, call it the camera server. It's a C++ application, and that is because the SDK of this depth camera came in with the language C++. But we're working with Python, so therefore creating a pipe to get the data from the camera to Python. And this side of the sequence diagram is all Python. This is C++. A pipe is a thing, a concept that's known for each operating system. I use specifically Windows pipes, but it shouldn't matter. You could also use other pipes on other operating systems if you care to run this setup on Linux or anything. So first create a pipe server. The Python code connects to the pipe. The camera server puts data on the pipe. Data is taken from the pipe by the camera client, and it gives the camera data to a data capture class, which applies some filters, as you've just seen, extracts the object from the images, and send each image separately to the neural network for it to classify, and then finally we draw the labels on the screen, as you have seen. So what we've seen is the can and the Buddha. Zooming in on this part, applying filters and extracting the objects, is here you have the camera. We get an image, which is first being cropped because the outsides of the depth camera image is not usable. Then, as you've seen, we subtract the background because we're not interested in the scenery, only interested in the objects which are put in front of it. And I will explain all these operations in more detail in later slides. Then a median filter to reduce noise. The contours are determined to know where objects are. Then the contours are evaluated with respect to their area size, and if they're too small, filter them out as noise and continue with the next contour, determining the bounding box, so we know the size of the object in the screen. Next we need to normalize the data or center the data, and that is shifting it in X, Y and Z axis, so in 3 dimensions the data is being centered. Then it's sent to the neural network, we get a label, and that's drawn on the screen. So into the image processing steps. First, as I've shown you, is we need to subtract the background. So you have a regular webcam, again, just for the reference. These images are not taken into the programming, into the software to classify the final image, just for our reference. Here you have a depth image, high on noise, and we take like 100 frames or so. And of each pixel across those 100 frames, the smallest value is taken. So what that means is the data that is closest to the camera is considered as the background. And then still you always have some noise that's left on the by the camera because it's just pretty noisy. So when we then put an object in the scene, as you see here in the webcam image, this is what it looks like from the depth camera, it sees that this is closer than the minimum values that we have established here, by which it knows that this is then the data that we're interested in, so that this is passed through to the final image that we're interested in. So now that we know where our Buddha is, kind of, we want to get rid of this noise because we want to make exactly sure where this Buddha is in this image. And when you apply some algorithm to find where this blob is, it gets more difficult the more noise there is. So we want to get rid of this noise, these white specks. So therefore a median filter is applied. And what's left is this completely black image with only the object of interest in the image. And you also see that these jagged lines of this Buddha statue become more smooth also by the median filter. And that's also good to average out the noise on the edge of the object. So as I've shown, it's working with multiple objects in the scene, and for that to work we need to do an additional thing. So if we would go from here, we could have centered this data and send it to the neural network, but if we have two images in the scene and we would send this to the neural network, we would have to train the neural network with this exact setup. So a chair here and a Buddha here, and it wouldn't be able otherwise to say there's a Buddha and a chair on the screen. But that is, of course, requires a lot of more training data, because the distance relative from each other can change a lot, can vary a lot, etc., etc. So therefore we need to apply the technique of finding the contours. So we go from this image, subtracted the background, reduce the noise by the median filter. Now we have this image, and then we ask the OpenCV library to find the contours. And we discard the really small contours. For instance, maybe small little things on the edges produce really tiny contours, but we get rid of those. So now we have these two objects separated from each other by their contour, but we're not there yet. We need this whole data of this chair to send to the neural network for classification, and also separately this whole data from the Buddha. So what happens then is, based on this contour, we create a mask. So fill it completely with white pixels. This is the mask. By having a mask, we can cut out this image entirely, and only this image, and feed that to the neural network. And also, when having these contours, having this mask, we can determine the bounding box, so we know where in this image is this chair, so we can later on put a label here to say this is a chair. So, as I said, the data needs to be centered. How does that work? So if you look on the left, and this plane could be, if you use your imagination, it could be what the depth camera is looking at, and this is the image that is there to process. And we have two objects in the scene, the red and the blue object. This green object and the cube are not in the scene. I'll tell you a bit about this later on. So we have this red object and this blue object, and you see that their locations in the scene differ, and also the size. Now what happens, just like finding these contours, we need to normalize this and send it to the neural network, or before sending it to the neural network. That is because we want to exclude the parameters of location and size when training the neural network. If we feed the neural network with a small object, it will be trained to recognize this small object. But we don't care about the size nor the location where it is in the image, only caring about the geometry and therefore what kind of object this is. So if we would have a large Buddha statue or a small, doesn't matter, it should label it as a Buddha statue, and also it should be irrelevant where we put it in the scene, it should still recognize it as a Buddha statue. And there comes this imaginary cube into play. And it's imaginary because this data is never really used, but it's just for visualization. So we have this red object and it's scaled to fit inside this imaginary cube, and it's brought all the way to the front. So if you imagine the depth camera to be here, then this would be 0 depth and this would be the furthest away. So each object is taken, brought all the way to the front to reach 0 depth and resized. If it's too big to fit in the imaginary cube, it's scaled down. If it's so small that it doesn't touch the edges of the cube, it's scaled up. And thereby each image becomes the same for the neural network to be trained with. So therefore we exclude location and size. Or thereby, I should say, thereby we exclude the parameters of location and size of the objects. And here on the right you see this Buddha statue, which is brought to the front and scaled like I just explained. And there you see that this is the part that was closest to the camera. This becomes completely dark. Just for some explanation, this is not actual data that's sent to the neural network, but this is normalized for us, so we can see some contrast. But in reality this is much more dark like this, with really low contrast. But I bumped up the contrast, otherwise we don't see the details. So now at this point what we have is we went from the depth image with multiple objects in the scene to normalized data that can be fed to the neural network. And as you can see, this is the data that's being sent, and the chair is as big as the Buddha. So that's what's meaning by normalizing and centering the data. The chair is much bigger in reality than the Buddha, but the chair is scaled down and the Buddha is scaled up to meet the edges of the bounding box, the bounding cube. So then when we have this separation of this data, each object is sent individually to the neural network, and the neural network returns the label which was used to train it with. And by knowing the bounding box that we determined earlier, visualized by this red line, we know where the object is in the scene, and therefore we can put the label on top of the bounding box, or wherever relative to the bounding box that you would like it to be, of course. Now something about the architecture of the neural network. This is pretty much a given. So what you always see with neural networks that process images is that you use convolution 2D layers. Also use some max pooling to lower the resolution. That's also often used. And finally you always need to flatten this data, because finally what you get is a single output layer where each node represents a label, a classification. So a chair, a Buddha, watering can, etc. So therefore you need to flatten this 2D structure to an array of values, which is then fed to some dense layers and some dropout. The dropout is used for generalization. So as I said, this is pretty much a given. You can play with the number of dense layers and you can play with the number of convolution layers, but this architecture is basically a given for this techniques to work with images. On the right you see then a rough visualization of the neural network, and with rough I mean I didn't put the dropout layers here, which are both there in training and both in execution of the neural network, but I didn't put them here for visualization. So what we have here is a convolution layer, dense, dense, dense. So just to give an impression of the complexity of all the connections that are at play when an object is being classified. Then we get to the point of training the neural network. So what goes into the neural network is a 16-bit image, grayscale image. And it's 16-bit because what we get back from the depth camera is millimeters. And if we would have 8-bit, it would be 0 to 255 millimeters, which is not that much. So it's 16-bit. And as you can see, it's only 128 pixels square. While the resolution of the depth camera is actually VGA, I didn't want to use that full resolution because it slows down the network tremendously, of course, because it needs to process a lot more data. So this is a trade-off. You scale down the resolution of the images so that you still have high enough accuracy and you get the speed of the network that you want. As I said, the network that I showed here in practice is trained with 7 classes, so it can recognize 7 different objects. And while training, I didn't use any validation because with the camera I don't need any validation. What I did use is the image data generator from Keras. So as I mentioned, Keras is the library used for the neural network, which comes with the image data generator. And what it does is it takes an image that I created myself first to train the network with. It takes the image and it modifies it a bit. It does that by scaling up or scaling down, skewing it a bit, a little bit of rotation, and I do that to create a bit of variation. And I do that to minimize the number of images that I need to properly train the neural network. For each object, I've taken 32 images. That's roughly 11 degrees change every time. So rotate the object 11 degrees, take an image, rotate the object again 11 degrees, take an image, until I get the full circle. So I have 32 images per class. But that's maybe not enough to train a neural network. So therefore use the image data generator, which creates more variation. So the neural network is being trained to generalize better on the data that it's given. And then only 32 epochs are used for training. Epoch is just another word for a train cycle, if you will. One-time training is an epoch. With a batch size which is unlimited. So all the data, stochastic gradient descent, all the data is put in the algorithm and at the end it's corrected by the learning rate. And training this on the GPU NVIDIA RTX 2080 Titan with 11 gigabytes of RAM takes less than a minute, so that's pretty fast. You don't need to wait half a day for this to train or to add another object. It can be trained in less than a minute. So then finally some comments on using real or virtual data. And by real data I mean images that come from the depth camera, so this. And with virtual data, I mean images that come from a 3D modeling application like this one, for instance, which is Blender. This black thing here represents the camera. And you can ask Blender to render an image, but not output color, but output depth, just like we have with the depth camera. And you see that this image, also normalized it to increase the contrast. This image is just nearly perfect. It doesn't contain noise, steep edges that a depth camera cannot see because they are too steep relative to the point of view of the camera, are not there because this is just nearly perfect. But this can be used to train the neural network. Also, first of course you need to subtract the background, etc., and normalize the data. But this can be used to train a neural network to recognize this Buddha statue in reality. So I've taken my own Buddha statue, used photogrammetry to produce this highly accurate model with all these tiny details and put it into Blender. So when you have a lot of images coming from the internet, a lot of models, you can actually use that to train your network to recognize those objects in real life. But what you cannot do is mix both virtual data and real data, because the real data contains the noise where the virtual data does not. So you need to use either real or either virtual data. Now we've come to the end of this presentation. I thank you very much for watching, and I thank also very much the people who worked on all this amazing software that made it possible to establish this hobby project. So I just quickly name Blender the 3D modeling application. OBS is the software I use to record this video. Visual Studio Code is a free IDE that I use to develop all this. Python, free programming language to use. Keras TensorFlow, also free for the neural network. And OpenCV, the library, that's completely free also, with all the image processing that I used for this setup. Thanks for watching. I hope you like it. Bye.